Bismillahirrahmanirrahim. Rabbi israh li sadri wa yassir li amri wa hlul 'uqdatam min lisani yafqahu qawli. Let's proceed our lecture to the next subtopic, which is motion in one dimension with constant acceleration. So as we know that acceleration is defined as delta v over delta t. For a constant acceleration, the V final equivalent to V initial plus AT. This is a commonly used by you all during your secondary level. Okay, if we want to interpret this into the graph, okay, you can see here, okay, for V versus T graph, okay, the slope of this graph give us the information of the constant A because it's only one value of A. That is why we call it as constant A. Okay, what does that mean by Vx final? It's here. Okay, it's equivalent to addition of Vx initial to the AT. In terms of graph, this is the meaning of your equation actually. Alright, so for constant A, we also can have the V average in terms of V initial plus V final divided by 2. Okay, because we know that the A is constant. That is why we can have V initial plus V final divided by 2. Okay, and when we have the graph of A versus T, because we have A constant, so that is why we have only one single line and there is no slope. Okay, there is no slope at all. Okay, because the A starting from T initial until T final, only one value of A because our A is constant. So let's recall the formula that we have for motion in one dimension with constant acceleration. We have V average previously in terms of delta x over delta t. We also may calculate the V average equivalent to V initial plus V final divided by 2. The displacement is x final minus x initial. The time interval or time taken to have that motion is T final minus T initial. Okay, and then for delta x equivalent to Vt, and the V is half of V initial plus V final. So we may rearrange, substitute here and there as we please, okay, as long as the concept is correct. Next, we have this equation, the one that very famous to you all. V final equivalent to V initial plus AT. Okay, if we want to substitute this into a formula of delta x just now, okay, we are going to substitute it for V final there, okay, with V initial plus AT. That is how we can have another equation of x final equivalent to x initial plus V initial t plus half AT square. Alright, this is only valid for constant A. Now, let's move forward with the other equation. We want to play around. We use this equation, okay, and rearrange it, make the T as the title, and now substitute into this equation. You are going to have another form of equation where we have this one, V final squared equivalent to V initial squared plus 2A delta x. Only applicable for constant A. We have all this, okay, when we have a constant A in terms of x. We may have the same form of equation in terms of y component. You just substitute the symbol of x with the y. And for the position, okay, and we may also have V y final equivalent to v y initial equivalent to simply vy, and y final equivalent to y initial plus vyt. This is only applicable whenever the ay equivalent to 0. So we have lots of kinematics equation. I believe you all already memorized this. Okay. In terms of x component given here, in terms of y component, let me list out for you. Vy final equivalent to Vy initial plus Ayt, okay, for the first version, and then Vy average, whether you are using AVG or you can put bar on the top of the V, also understood. It's Vy initial plus Vy final over 2. And for position, got that part. And for position, y final equivalent to y initial plus half, okay, Vy initial plus Vy final times with a t, right? And then another form for position as well, equivalent to y initial plus Vy initial plus half Ay t square. And the final version of the Vy final squared equivalent to Vy initial squared plus 2Ay y final minus y initial. All of this equation only applicable for constant acceleration. If you deal with the instantaneous acceleration or instantaneous v, remember you have to do the tangent line to the position needed or the time needed accordingly, and then calculate the slope of the tangent line. That will give you whether instantaneous velocity or instantaneous acceleration. Example 2.4, okay, a race car starting from rest accelerates at a constant rate of 5 meter per second squared, very fast. A, what is the velocity of the car after it has traveled 1.00 times 10 to the power of 2, means that 100 feet. This is CGS unit. How much time has elapsed? Calculate the average velocity two different way. Okay, so we know that the V initial of the car 0 at x equivalent to 0. Okay, whenever it reached 30.5 meter, what is the V of the car? The question asking for, right? And then finally we need to calculate the time taken and average velocity two different ways. Okay, so let's answer for part A. First thing first, we need to convert the delta x from CGS to SI unit. So this is a conversion factor. Alright, so you will have the final position interval of 100 feet is 30.5 meter. That is how we put the information here. And then we're going to use the formation of V square, equation of V square equivalent to V naught squared or V initial squared plus 2A delta x. Don't be confused. Sometimes we may use V initial, sometimes we may put at as V naught. It's the same thing, representing initial. So if we refer to this, if we are using naught, normally for V final, it has no symbol. Okay, it's a pair. But if you are using V initial symbol, okay, VI, here will be VF, stand for V final. Alright, so by make use of this equation, we want to know the V, so square root of V naught square plus 2A delta x, substitute all the information given. V0 is 0 and the A is 5 and the delta X is 30.5 meter. You will have the V final is 17.5 meter per second. For part B, how much time has elapsed? Okay, we are going to use the equation that where we have most of the unknown. The only unknown that we're going to solve is the T. So we have V equivalent to V0 plus AT. Put the T as the unknown, the V0 equivalent to 0. Okay, so V final already calculated as 17.5. So you see, you will solve for T. You will get your T 3.5 second. Okay, now for C, calculate the average velocity in two different ways. So we have this equation, the first version, and the second version of it. Okay, so V average is delta X over delta T. We have 8.71 meter per second. And in terms of V average, V initial plus V final over 2, you have 8.75 meter per second. So it's slightly different and yet not much. Okay, slightly only. Right. So do the exercise 2.4. Take it as your homework. We shall discuss this in our class. Okay, now example 2.5, a car chase. Okay, a car traveling at constant speed of 24 meter per second passes a trooper hidden behind a billboard, as in figure. Okay, 1 second after the speeding car passes a billboard, the trooper set off in chase with a constant acceleration of 3 meter per second squared. How long does it take the trooper to overtake the speeding car? B, how fast is the trooper going at that time? Okay, so take a look on the strategy here. Solving this problem involves two simultaneous kinematics equation of position, one for the trooper and the other for the car. Choose T equivalent to 0 to correspond to the time the trooper takes up the chase when the car is at X equivalent to 24 meter because of its head start. So this is V times T. Give us the X initial of the car already at 24 meter at the moment of the trooper set off. The trooper catch up with the car when their position are the same. This is the minimum requirement to overtake. Okay, to have overtake. At least the final position of the two, the car and the trooper are the same. Then the trooper may overtake the car. This suggests setting of final position of the trooper equivalent to final position of the car. Okay, and for solving for time, which can then be used to find the trooper speed in part B. How long does it take the trooper to overtake the car? So we need to write the car equations for the displacement. The delta X for the car is equivalent to X final of the car minus X initial, equivalent to V naught T plus half AT square. This is for the car. Rearrange the equation, make the X final of the car as the title for this equation. Okay, and initial position of the car already 24 meter. Why is it? We are going to set again the T equivalent to 0 at the moment the trooper set off or moving. So means that after 1 second the car already passed, isn't it? So after 1 second, within that 1 second, how much the distance already traveled by the car? So this is the way we calculate, because given to us the speed of the car, okay, 24 meter per second. So within 1 second the car already traveled 24 meter. That is how we know the initial position of the car, 24 meter in front of the trooper. Remember, the trooper going to be our reference. So this is V initial, this is X initial of the car, and this is the V of the car. because it's constant speed. So V initial of the car is the same to the V final of the car. Okay, it has no acceleration, right? So we can simply put the A of the car as 0. And bear in mind, V final of the car equivalent to V initial of the car, right? That is how we know the V final of the car is also 24 meter per second. Then, now we're going to set the equation for the trooper. We're going to use the same equation to this. However, we're going to substitute the subscribe with the trooper. Okay, and V initial of the trooper is 0. Okay, and initial position of the trooper is 0. V initial of the trooper also 0, and the trooper has A, amount of it is 3 meter per second squared. So if you substitute to the equation of the trooper, you will have final position of the trooper is equivalent to this one going to be 0, isn't it? This one going to be 0, and this one going to be 0. We're left with the half A trooper T squared. See, you will have this amount of equation. Next step, we are going to set the final position of the trooper equivalent to the final position of the car. Okay, that is a concept for the trooper to overtake. Minimum requirement for the case of trooper to overtake the car. So when we do this, we are going to have this equation. So this is X final for the trooper equivalent to X final for the car. So you substitute the two equations that already constructed in previous slide just now. Okay, we will have this equation. Then we're going to solve for the T. You see, you will have your T 16.9 seconds. This is the time, okay, taken or needed for finally the trooper at the same position to the car. Okay, so part B, you need to find the trooper speed at that time. So again, you're going to substitute the equation to the V equivalent to V0 plus AT for the trooper. V0 of the trooper, V initial of the trooper is 0. So substitute the T here, you will get V final of the trooper is 50.7 meter per second. Exercise 2.5, going to be your homework again. Do it, solve it. We shall discuss this in our class. Let's move to example 2.6. A typical jetliner lands at the speed of 1.6 times 10 to the power of 2 miles per hour and decelerate at the rate of 10 miles per hour per second. If the plane travels at a constant speed of this for 1 second after landing before applying the brakes. Why it cannot apply the brakes straight away? We need to have at least reaction time, right? 1 second is the reaction time. What is the total displacement of the aircraft between touchdown on the runway and coming to rest? So this is the key of V final for the aircraft become 0. V final 0. Okay. So take a look on the solution given. V initial, we need to convert it first because given to us in terms of CGS unit. So this is a conversion factor, and then this is the SI unit of your V initial, as well as the A, you need to convert it first. And there is negative sign. Why is it? Because it stated there it is decelerate. Here, decelerate. Okay, and then by using delta X equation, delta X equivalent to V initial T plus half AT square. Okay, substitute V initial equivalent to this, and the T taken is 1 second. And the A is equivalent to 0. This is before the brakes is applied. Therefore, there is no deceleration yet. Okay, so you will have the delta X of coasting before the brake is applied, 71.5 meter. Okay. Use the time-independent kinematics equation to find the displacement while the plane is braking. So now the brake already applied. Okay, so we're going to have the equation of V squared equivalent to V naught squared plus 2A delta X of braking. Okay, why we are not using the equation that has T, the time? Because we don't have the information of the T. Okay, so we have to figure out any other equation that we can fulfill all the information only with one unknown without the T. If you are using equation with the T, you are going to have two unknowns within one equation, so it is unsolved. Alright, so from here you're going to calculate the delta X braking, give you 572 meters. And finally, you are going to total up the coasting distance, displacement, and also the braking displacement, give you the information of 644 meters. Okay, for the exercise 2.6, take this as your homework. So inshallah we will discuss the solution for this exercise in our class. That's all from me. Thank you very much, and Assalamualaikum warahmatullahi wabarakatuh. See you.